NENOMATICA, where mathematics meets YouTube excellence. Example, we will solve the system of linear inequalities in one variable, then visualize the intersection on a number line. Rule, solve each inequality separately, then take the intersection of solution sets. Step 1, solve each inequality. First inequality, since the coefficient 3 is positive, we divide both sides by 3, and the inequality direction does not change. That gives x is greater than 1/3. So the first solution set is the open interval from 1/3 to infinity. Second inequality, when multiplying or dividing by a negative number, flip the inequality sign. Here, negative x less than 3 implies x greater than negative 3. Thus, the second solution set is the open interval from -3 to infinity. Step 2, intersect the sets. Take the common values of d sub 1 and d sub 2. The stricter lower bound is 1/3, so the intersection is the open interval from 1/3 to infinity. Here is the problem in bold orange: 2x less than square root of 5 and minus x greater than 1.6. Step 1. We apply the rule. Ax less than b implies x less than b over a. Start with 2x less than square root of 5. Divide both sides by 2, a positive number, so the inequality direction stays the same. This gives x less than square root of 5 over 2. We record the first solution, set d1 as the interval from negative infinity up to square root of 5 over 2. Then, we also show it on a number line. Step 2. We use the negative coefficient rule. Minus x greater than implies x less than negative a. Start with minus x greater than 1.6. Multiply by -1, flipping the inequality sign. We get x less than negative 1.6 and record d2 as the interval from negative infinity to negative 1.6. We will graph it as well. Quick challenge. Why did the sign flip when multiplying by -1? Step 3. Now we intersect the two solution sets. d equals d1 intersection d2 equals the interval from negative infinity to square root of 5 over 2 intersect the interval from negative infinity to negative 1.6. Since negative 1.6 is less than square root of 5 over 2, the intersection is from negative infinity to negative 1.6. We will show the intersection on a number line, and then present the final answer with a celebration. Final answer: d equals open interval from negative infinity to negative 1.6. Summary: we solved two inequalities in the exact order of the reference steps, found d1 and d2, and intersected the sets to get the final solution. Example: we will solve the system of linear inequalities step by step, following the exact sequence shown on screen. Step 1. Solve the first inequality. Start with x minus 8 is less than 2x minus 1. Move all x terms to the left and constants to the right. We get negative x is less than 7. Multiply both sides by -1, and remember to reverse the inequality. So x is greater than -7. The first solution set is open interval -7 to plus infinity. Step 2. Solve the second inequality. Start with 2x minus 1 is less than -5. Add 1 to both sides. 2x is less than -4. Divide both sides by 2. Then x is less than -2. So the second solution set is open interval minus infinity to -2. Step 3. Intersect the two sets. Intersect the two sets. The final solution is the intersection of d sub 1 and d sub 2. That interval is open from -7 to -2. Example: we will solve the system of inequalities shown in the image step by step, following the exact algebraic moves displayed. Step 1. Solve the first inequality. X minus 1 is less than 2x minus 3. We use the rule add or subtract the same quantity on both sides. Move all x terms to one side and constants to the other. Simplify to negative x is less than -2. Divide both sides by -1, and remember to flip the inequality. This gives x greater than 2. Step 2. Solve the second inequality. 2x minus 3 is less than -x over 2 plus 1. We will add x over 2 to both sides, and add 3 to both sides. That gives 2x plus x over 2 is less than 1 plus 3. Express with a common denominator. Combine like terms to get 5x over 2 is less than 4. Multiply both sides by 2/5 to isolate x, and obtain x less than 8/5. Step 3. Combine both conditions. We need x greater than 2 and x less than 8/5 simultaneously on a number line. These intervals do not overlap, so the system has no solution. Summary: we solved each inequality exactly as shown, obtained x greater than 2 and x less than 8/5, and confirmed on the number line that there is no overlap. Therefore, the system has no solution. We will solve a system of two linear inequalities exactly following the algebraic algorithm shown. We will keep the exact order of steps from the source. First, we solve the left inequality completely to obtain the domain D sub 1. Then we solve the right inequality to obtain D sub 2. Finally, we intersect the two sets to get the final solution. Step 1. Solve the first inequality. We use the rule for linear inequalities. Collect x terms on the left, constants on the right, respecting operations on both sides. Quick challenge. Pick any number less than 2/27, like 0, and check that it satisfies the first inequality. Step 2. Solve the second inequality. Again, we use the linear inequality rule. Collect like terms and scale both sides by positive numbers only. Another quick challenge. Choose a number greater than -9/14, like 0 again, and verify it makes the second inequality true. Step 3. Intersect the two solution sets. The final answer is D equals D1 intersect D2. We will also illustrate the interval on a number line. Therefore, the solution of the system is all real x strictly between -9/14 and 2/27. We display the problem in bold. The original solution shows two paths. Method 1 splits the compound inequality into two separate ones and intersects the solution sets. Method 2 manipulates the compound inequality directly, adding the same number to all three parts and then dividing. Method 1, split and intersect. We create the system 3x minus 2 greater than or equal to 1 and 3x minus 2 less than 7. From the first inequality, 3x greater or equal 3, so x greater or equal 1. Call this set D1, the interval from 1 close to infinity. From the second inequality, 3x less than 9, so x less than 3. Call this set D2, the interval from -infinity to 3 open. The solution is the intersection of D1 and D2, the interval from 1 closed to 3 open. Method 2, operate on the compound inequality directly. Start with 1 less than or equal to 3x minus 2 or equal to 3x minus 2 less than 7. Add 2 to all three parts. Highlight the changes. Simplify to 3 less than or equal to 3x less than 9. Divide every part by positive 3. Directions stay the same. Simplify to 1 less than or equal to x less than 3. Conclude x belongs to the interval from 1 closed to 3 open. Final answer x is in the interval from 1 inclusive to 3 exclusive. Here is the problem statement. The word example appears. Then the chain inequality in bold orange. Step 1. Split the chain inequality into two separate inequalities. We will solve each one and then intersect the solutions. We start with the right inequality. First distribute the 3. Then collect like terms to isolate x and solve. This gives x greater than or equal to 5. Now solve the left inequality. Distribute the 3 on the right, then bring variables to one side and constants to the other. When multiplying or dividing by -1, flip the inequality sign. We obtain x less than or equal to 12. Finally, intersect the two solution sets. The intersection of x greater than or equal to 5 and x less than or equal to 12 is the closed interval from 5 to 12. Quick challenge. Could you solve a similar inequality like 4x minus 1 greater? Example. Solve the system of inequalities exactly following each algebraic step. Step 1. Solve the first inequality. We will clear the fractions by multiplying both sides by 12, the least common multiple of the denominators 6, 4, and 3. Then we distribute and simplify to get a cleaner inequality. Step 2. Expand and simplify. Distribute the -3 across the parentheses. Combine like terms to see the structure more clearly. Step 3. Isolate x. Move terms so x is on one side. Then divide to obtain the solution set for this branch. Step 4. Solve the second inequality. Again, we clear fractions by multiplying both sides by 12. Then we simplify. Step 5. Expand and simplify by distributing and combining like terms. Step 6. Isolate x to complete the second branch. Step 7. Take the intersection of the two solution intervals. The overlap is all numbers less than -3. Therefore, the final solution to the system is x less than -3. Congratulations! Summary. We cleared denominators with the... Here is the example. Step 1. Expand the right-hand side, then collect like terms, and finally solve the resulting simple inequality. Step 2. Factor out 5 to the x. Use the positivity of the exponential for all real x, and conclude the condition on x. Step 3. Expand the right-hand side. Cancel equal terms on both sides. Recognize the tautology 0 less than 2, and obtain the full real line. Finally, intersect all three sets to get the solution set. Summary. We expanded, collected terms, respected inequality rules, used exponential positivity, and intersected sets to get the single solution x equals 1. Example. Below the example, we show the system to solve. We first visualize the extracted formulas as bold latex. 5x plus 8 is less than 3x plus 14. -1 is less than or equal to 2x minus 5 and less than 9. X minus 1 is less than the fraction x plus 4 over 2. Step 1. We use the rule for linear inequalities. Move like terms to one side. Subtract 3x from both sides and subtract 8 from both sides. 2x is less than 6. Divide by 2 to get x less than 3. Thus, d sub 1 equals open interval -infinity to 3. Step 2. Use the compound inequality rule. Add 5 across the entire inequality. We get 4 less than or equal to 2x and less than 14. Divide every part by 2. Therefore, 2 is less than or equal to x, and x is less than 7. So, d sub 2 equals the half open interval 2 to 7. Step 3. For a fraction inequality with a positive denominator, multiply both sides by 2. 2 times x minus 1 is less than x plus 4. Rearrange to get x less than 6. Therefore, d sub 3 equals open interval -infinity to 6. Quick challenge. Predict the final intersection before it appears. Step 4. The solution of the system is the intersection of sets. Intersect -infinity to 3 with 2 to 7. Then intersect the result with -infinity to 6. We obtain the final set from 2 inclusive to 3 exclusive. In this video, we will solve a system of linear inequalities step by step. Step 1. We solve the first inequality. Start by moving all terms to the left and comparing to 0. Now separate the constant. Compare the fractional terms. Multiply both sides by -2 and remember the direction flips. Therefore, the first solution set is d1 equals open -1 to infinity. Quick challenge. What would change if the inequality symbols were non-strict, that is, less than or equal instead of less than? Step 2. We solve the second inequality by finding a common denominator. Now move from the fraction to a simple inequality. Hence x is less than 2, and we label the solution set d2. Step 3. The solution to the system is the intersection of d1 and d2. Therefore, the solution of the system is the open interval from -1 to 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.